Hi guys, welcome back to the channel. Today we'll be talking about orphan and zombie processes. Let's get started. Once a process is forked, there should be some mechanism for the parent to be able to know the status of the child, right? Parent should be able to know when one of its child processes changes state or the child terminates or is stopped by a signal. It is always useful for the parent to be able to monitor the children to find out when and how they terminate. I have drawn a diagram here to explain the situation better. A process A with a process ID of 100 has invoked fork, which results in creation of a new process with process ID 200. Both the processes now execute independently. Both of them are doing some work, and parent has called exit or has died unexpectedly here. There could be multiple reasons that we'll discuss later, but we can see while the child was executing, the parent has terminated. There is no parent for this child process, and that is why we'll call this process as orphan process in this context. The child would then continue its execution, and after some point, it can also terminate and call a exit. The point at which the process becomes orphan, it is adopted by a init process. So if you run a get parent process ID after its original parent died, you would get a return value of 1 for this system call here. But why is init adopting this process? Can't we really let it run and exit on its own? Yeah, that is possible, but it would waste system resources. Kernel has to hold the exit status of all the processes in process table. And the only way this entry could be freed is by calling a system call called wait. Now, in this scenario, it would be the responsibility of the init process to call wait on this children and remove the kernel table entry to free all the resources. There could be another scenario where child has died while the parent was still executing. In this scenario, the child process is not an orphan, but it has become a zombie process once it has died. The kernel would hold its process ID, its termination status, and resource usage statistics in its process table. This entry in the process table would clear only once parent calls wait for this child. Once wait is executed, the parent retrieves the termination status, and this entry is then removed from the kernel process table. Let's assert this understanding once again with the example program. I'm copying the previous fork program that we had written and I'm going to modify the same. Let's remove the unwanted lines. I'll be printing the child process ID in case 0 and we'll be giving a termination status of 200 in the child process. I have added a sleep of 5 seconds to let the child finish first. I'm creating a command string where I'm grepping the output of the PS command with the program name. argv0 is always the name of the running program, and basename is a API that can be used to extract the string equivalent of this. I am passing the command string as an input to system API. Now let's call wait and retrieve the status of the terminated child. This would update the status integer variable with the exit status of 200 in the parent. Let's see what is the output now. The output seems to be intermingled. There is an interesting concept that we'll talk about later, which causes the printfs to be buffered in the standard output library and flushed only when the program exits, due to which system command is printing its output first and at the end printfs are being flushed. We can disable the buffering with call to set buff, and we'll discuss more about it in future video. I have added new line characters in the printf. Let's see what the output is. Parent process ID is 3229 and child process ID is 3230. There is a defunct entry for the zombie process, whereas after wait it has been cleared out. Let's also talk about a scenario where child does some heavy task that takes 100 seconds. To depict that, I have added a sleep of 100 seconds on line number 24. The parent, which had to do some important task on line number 40, would not be able to do until it completes the wait call on line number 39. It will be blocked on line number 39 for 100 seconds until the child completes. There should be a mechanism to indicate that the child has terminated, isn't it? Let's understand this better with the help of the diagram. At this point, the process has become orphan and it has terminated at this point. Whenever the child terminates, it delivers a sick child signal to the parent. Now, in this scenario, since the process has been adopted by init due to parent being dead, the signal is delivered to the init instead of the original parent. If A would have lived long enough, A would have received this sick child signal. In nutshell, the parent always receives a sick child signal whenever its child terminates. And this signal is delivered for each child. So for example, there are 100 child processes. The parent would receive 100 sick child signals on each child termination. In this scenario, signal handlers would be of great help. Instead of blocking on wait system call in the parent, waiting for the child to terminate, we can establish a signal handler which would be invoked once sick child is sent to the parent, and we can perform the wait inside the signal handler. Sick child by default is ignored in the parent process. We have to establish a signal handler to be able to catch sick child and perform wait inside the signal function. I am adding a sleep of 2 seconds in the child process to not let the child finish quickly, and that allows the parent to establish the signal handler. Although this is not the correct way of handling sick child, but for understanding, we are going to do it this way. With the help of signal function, I am instructing the OS to run handle terminated child function once sick child signal is received. Inside handle terminated child function, I can invoke a wait that will clear any zombie entry in the kernel process table and free all the resources. Let's look at the program output now. There is no zombie defunct entry in the PS output as the parent process is reaping the child process as soon as it terminates. Although this is not the correct way of reaping the child process because there are caveats associated to this approach. If there are multiple child processes that terminate in quick succession, then there are chances that sick child of some of the child processes could be missed when the signal handler is being run. This is the default behavior of the signal handler function. If multiple sick child signals are delivered while the signal handler is being run, then those sick child signals are not queued. To reap multiple child processes, we can block the sick child signal before going into the signal handler and unblock the sick child signal once we come out of the handler. This method ensures that all the sick childs that were delivered when the handler was running are re-delivered once the sick child signal is unblocked. This could be achieved with sick suspend system call, and we'll discuss about it in one of our future videos.